This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
We talked a little bit about, the intricacies of these patterns, antenna patterns, and we said, well, if we're looking at an antenna pattern, usually it has the major lobe, which is where most of the radiation is radiated from. We said that there are also side lobes, which are not as strong as the main lobe. And we also briefly talked about the back lobe. We talked about half power beam width, and that is where the beam width, the power in the beam is down 3 dB, and that actually tells us roughly what that beam width of that antenna pattern is. We then went on and talked about the various radiation fields of an antenna. We said, depending on where we're at in an antenna or how close we're of an antenna, we define that there's a near field. And we said specifically, if you're designing a PCB board and you're in the near field, anything that's in the near field actually affects the antenna and becomes part of the antenna, and actually affects also the, if you put something in an antenna's near field, it affects the antenna, it also affects the radiation pattern, it affects a whole bunch of things. So whenever you're designing an antenna or putting an antenna on a PCB board, make sure that you put things away or out of its near field. We also talked about the far field, and that's regions which are far away from the antenna. We've also got a definition for the far field. And we said specifically, if we're in the far field, there's a relationship between the electric field and the magnetic field, and they're related by the wave impedance. Okay? We then went on and we talked about power density, and we defined Poynting's vector. And we worked out that the total power is the integral over a surface the Poynting vector integrated over a surface gives us the total power, right? So if you've got a power density, if you integrate over a surface, it gives you the total power, right? And then we went through and we defined directivity of an antenna, right? And we had the formal definitions, where we said, look, if you want to work out the antenna directivity, you can actually, and if somebody gives you the radiation intensity, or if somebody gives you the actual power, or gives you the Poynting vector, you can actually do that, and you can go through the whole process of being able to determine that. But sometimes, being engineers, we don't want to do that because it's complex, it's time-consuming, and sometimes you want quick and dirty answers, right? And that's where I said, well, guess what? If we want to work out the directivity, there are some approximations, and one of the approximations, rough approximations, which you can, have in the back of your mind when you're doing this, is the directivity is roughly, 41,000 on the half power beam width in the azimuth and elevation. All right, so you look at the antenna pattern, it looks like a cone, and you say, well, if it's 30 degrees in this half power bandwidth in this direction, 30 degrees in this, I can work out its directivity. Or if it's a 1 degree beam, in azimuth and elevation, I can also work out its directivity using this equation, right? It's a quick and dirty approximation, right? Rather than going through the formal machinery in order to work out what the directivity is. That's all that was about. And lastly, what we did is we showed that we defined gain of an antenna to be the directivity multiplied by its efficiency. And we made sure that we did not, that the efficiency accounts for only the power that's accepted into the antenna. It's not the power that's incident on a port, it's actually the power that's accepted into the port, which is absolutely key here in working out the efficiency. So that's what we talked about last week. And now let's go through and talk about more about antennas, and we'll talk about okay, so did we do the example? Does anyone remember? So we talked about antenna efficiency, is that correct? Okay, so let's start from there and we can go from there. Okay. Okay, so we talked about antenna efficiency, and then just to re-emphasize, antenna efficiency is the power that's actually transmitted out of the antenna structure, right? It's all of the power that's incident, or not incident, that's actually accepted by into the antenna port, to the ratio that's actually radiated. And we said that there are losses in that antenna structure which are related to essentially either dielectric or metallic losses. Can anyone give me an example of a metallic type loss that we would expect in an antenna? Okay, so you've got metal. What are one of the losses in metal? Heat due to resistance. Perfect. All right, and dielectric loss, and also dielectric loss. Okay, so when we're working out the antenna efficiency, the difference about when we're looking at antenna efficiency is we also look at the reflection and mismatch losses. I know you've probably seen this before, but we're going to go into much greater detail in about 2 lectures' time, where we're going to talk about transmission lines and look at all the properties of transmission lines. But there's this concept called reflection coefficient. Who can remind the rest of your colleagues what the reflection coefficient is? If you had a transmission line, and I tell you it's got a reflection coefficient, what does that mean? Anybody? Who doesn't know what a reflection coefficient is? You don't? Okay. So essentially, what we'll do is in transmission lines, when the impedance isn't matched, like when you're looking at a piece of glass, because the impedance of there is 377 ohms and the impedance of glass is something else. When you look at glass, you can actually see a reflection, right? Because not all this light goes through it, right? Similarly, when you've got mismatches in impedance on transmission lines or in surfaces, some of the energy is reflected and some of it's transmitted. So the reflection coefficient actually tells you the amount of energy that is reflected back to the generator. Okay? And what we were saying previously was, when we were looking at gain, we did not look at antenna reflection coefficient, but when we're looking at efficiency, we also need to take into account the reflection coefficient, which is essentially this is a definition. We'll talk specifically about the reflection coefficient and how we derive it in 2 lectures' time. Okay? So let's do a short example. Okay. And the example is as follows. Okay, so we've got a half wavelength dipole antenna. Who knows what a half wavelength dipole antenna looks like? Yes, the person that's drawing it. Yes. Yeah, it's literally, and a dipole antenna is literally, you can almost think of it as a coat hanger. You can almost make a coat hanger, a dipole antenna out of a coat hanger. You've got 2 pieces of wire and they're asymmetrical. And half a wavelength means that this distance is lambda on 2. Okay, so that's a dipole antenna. And we say that it's got an input impedance of 73 ohms. Okay, and what we'll do is we'll derive and work out how we can actually calculate the impedance of these dipole antennas later on. But at the moment, let's assume that somebody's given you the data that says that this antenna has an input impedance of 73 ohms. And let's, for argument's sake, say we're connecting the generator to the dipole using a transmission line, and this transmission line has an input impedance of 50 ohms. All right? What I'd like you to do, and we'll calculate this, but anyway, somebody's also given you the radiation intensity is equal to B0 sine cube theta, right? Now, you can actually work out the radiation intensity by working out the Poynting vector and, you know, working E cross H, multiplying by R squared and doing the integral. But for argument's sake, let's say somebody gave you this information so you don't have to do the calculation. So the question is, let's find out, or the question that might be on an exam is find the maximum gain of this antenna, and also let's find the efficiency of this antenna. Okay. So we remember that the directivity is 4 pi U max on P rad, which is the total radiated power. And if you go through the calculations, you can actually show that U max here, if it's sine cubed theta, what's the maximum value of sine cubed theta? 1. Right, perfect, 1. So the maximum of U is B0. If we do the integral of that, so it's sine to the 4th theta. Now you can, usually in an exam or whatever, I'll give you some tables so you can actually look it up, but if you saw sine to the 4th theta integrated from 0 to pi, and then 0 to 2 pi, what you can actually show is that is equal to B0 3 pi squared on 4, and if you plug all this in, what you find is the directivity of a half wavelength dipole is 1.697 or 1.7, and if you take the log of that, you can actually work out what it is in dB. Now I ask, what is its efficiency, right? And we said the gain is ECD, which is the dielectric and the resistive losses times the gain. If I said that it's lossless, what does ECD equal to? 1, right? Because there's no losses. Okay, so therefore the gain is equal just to the directivity, okay? And then if we look through, and I said what's its total efficiency? Well, of that antenna, we say the total efficiency is equal to the ratio of the power that's actually absorbed into the port multiplied by the losses in the dielectric and the resistive losses into the antenna. We said that ECD equals 1. We can work out what ER is, right, which is the amount of power that's actually absorbed, right? And we can show that that's 0.965 if you do through the calculations, because you say, well, the load of the antenna is 73 ohms. We hit the transmission line is 50 ohms. We can actually work out the reflection coefficient. We work out what ER is. So therefore, the total efficiency of this antenna is 0.965, which is a pretty good number, or 0.15 dB, 0.155 dB loss. Okay, that's an example of how to be able to work out the efficiency of an antenna. Okay, now we'll introduce another concept which we've talked about briefly, but I'll go into a little bit more details, and that is antenna polarization. And a few seconds ago when I was doing the review, sorry, or maybe a couple of minutes ago when I was doing the review for lecture 3, I said, well, polarization is essentially the plane which the E field lies in, right? So can anyone tell me what do they think are some examples of polarization of antennas? Right, so you got the most trivial one, right? Suppose the E field's up. What would you call that? Linear. Sorry, linear and vertical, right? Yes. Because linear's got multiple, so it could be, and then how about if I did this? If I turned my dipole around horizontal. Perfect. What happens, it wouldn't be a dipole, it would be essentially a patch antenna. Who's seen a patch antenna? You've seen them on PCB boards, right? So they do something like this, right? And essentially what you do, this is the microstrip line, and this is the radiating structure. Usually you cut this section off, and you cut this section off a little bit. And what happens is it generates an electric field which varies with time. It actually spins around, right? Can anyone tell me why would anyone in their right mind want a circularly polarized antenna? Yeah.
You don't have to align the receiving antenna.
Perfect. Everyone got that? Yes? No? No. Okay. Suppose I've got my mobile phone, right? And I've put and it's got a dipole in it, right? And the dipole's vertically polarized. Okay, so therefore the electric field goes up and down. And I'm talking, right? You know, we chatting. Okay, so you guys probably WeChat or whatever rather than talk, right? And you're doing this. But then all of a sudden you see some nice pictures and you want to do it in this mode, right? All of a sudden the polarization is 90 degrees out, right? So therefore what we'll show is if you've got, it's never true, but if you had a perfect antenna, what would happen is if you crossed the polarizations, you would get no signal, or you get a huge loss. They can come in, wait a sec. You can come in this way if you want. Oh, sorry. No, somebody else. So if you crossed the polarizations, what it would mean is that you would get infinite loss in signal, right? Or the signal will go to zero, right? So therefore, an antenna never has, and I haven't defined this, an actual ratio of an antenna is never infinity, right? It's only just 6 or 7 dB. But nonetheless, what it means is if you change the orientation of your phone, what would happen is the antenna would drop out, the signal would drop out. So in order to not have that loss, that this huge amount of loss, usually what you try to do is to have an antenna which has a polarization which varies, which is not on one particular axis. It actually spins around the two axes. And as a consequence of that, it means that all of a sudden, even if you change the orientation of your phone, you can still maintain communication with the base station, right? And that's the reason why you use circularly polarized antennas. Now, what's the disadvantage of using a circular polarized antenna? Yes?
At some points you don't get any signal, so it was spinning and you align it vertically, and at some point in time it's horizontal, but not going to be...
No. What I was going to say is because you're never perfectly aligned, you've always got a 3 dB loss, right? Okay, so that's the disadvantage of being circular polarized, that you're always suffering a 3 dB loss, but the advantage of doing that is that you never drop out completely. So you can say, well, I lose 3 dB, but I don't really care because I never suffer the worst case, right? So yes, maybe I can't get my WeChat as far, but you know, if I'm connected to a base station, I can always get my WeChat, right? Because it doesn't matter how I'm orientated. Okay. And this is essentially talking about if we got a dipole, I've mentioned this before, the E plane, which is the polarization, is parallel or is essentially in the same plane as the dipole, because you've got the difference in the voltage, which is the direction of the electric field, and the H plane is perpendicular to that. And we've talked about circular polarization. Now, in circular polarization, life's never easy, right? There's left-hand polarization and right-hand polarization, and depending on how it spins around, you can have two different types of polarization. And the reason why I mention that is depending, and this is not examinable, but I'll mention this anyway, just so that it motivates you to say, why is Stan telling us all this stuff? Why is he wasting our time? You know, we could be out there, I mean, albeit the weather's terrible today, we could be out there doing something better rather than listening to Stan talk about antennas. And the reason is, if you've got right-hand polarization and you reflect off a metallic surface, what happens is it changes the polarization. So you go from left to right, whereas a dielectric, it maintains the polarization. If it's left, and if it's right, it's right. Off a dielectric, on a metallic surface, you go from left to right. It's like looking into a mirror, right? And that's where you then need to look at, you know, how do you deal with that situation? Now, and I apologise for the terrible writing here. So what I'm trying to do is work out the polarization factor, and the polarization factor is essentially the inner product, right? So what I'm trying to do is work out what's the inner product of these. If I've got a particular field in a particular direction and I'm in a different polarization, what's the power loss that I get, or the polarization factor? And because it's power, you square it rather than using your dot product, right, which is just cos theta. That's all I'm doing there. And let's go through an example, okay? And here, what I'm showing is, suppose you've got a polarized wave, and it's on the x-axis, all right? No big deal. It's a polarized wave, it's traveling, and its electric field is aligned with the x-axis. And suppose I've got an antenna, right? And all I'm doing here is I'm saying that the antenna polarization, I'm writing it in terms of A and B's, right? And the reason why I'm writing it in terms of A's and B's is to say, well, if I have A equals 1, B equals 0, it's polarized in the X. If it's X is A, X is 0, B, A is 0, B is 1, it's polarized in the Y direction. Okay, that's all I'm doing there. And what I'm saying is, if you go through this process and you just say A equals 1, B equals 0 is vertical, or another example, A equals 0, B equals 1 is horizontal, you work out the polarization factor. Because in this particular case, they are collinear, or they're aligned. The polarization factor is 1, whereas if they're crossed, the polarization factor is 0. Right? So therefore, it just says, hey, don't try to pick up a linearly polarized signal with a with a horizontally polarized, antenna. And who of you uses AM radio stations, or I guess that's probably prehistoric for you guys. Yes, you do, in the car, or maybe not AM, but you definitely listen to FM, right? In the car, you don't listen to the radio? No? Finding it shocking. Sorry? All right, okay, fine, okay. But the point is, that's why, I mean, in the past, you would laugh, in vehicles, they used to have an antenna, you'd switch it on and this wire would come up. Had anyone seen any of this? And that was so that it was linear, so therefore it would match with your car, with the AM transmitter, right? So therefore it'd be large. It was a monopole, and it would, in its polarization, would match with the transmitter radio station. So therefore you could actually get pick up the signal. Now what happens is FM transmitters. It's the same concept, but at least on cars you can say, they've designed slightly different antennas in order to still give you that performance. Anyway, that was a long time ago, but the concepts still exist. And if you were designing a, how do you call it, an antenna, you would still need to worry about all these things. Now, I'm going to go on and talk about two other critically important components for an antenna. Okay. So the first one is, usually we've got an antenna, and an antenna, if you plug in a vector network analyzer, who knows what a vector network analyzer is? You must have used that in the lab. Come on. Let me call BS on that. No? All right. So if you wanted to work out the impedance of something, how would you measure it? How did they teach you to measure it? Sorry? Yeah, but that only gives you resistance. So how do you get, you can get R, right? That'll give you the impedance or resistance. How do you get the other impedance? And how do you get it at different frequencies, right? Because technically, I'm writing this as something that's frequency independent, but really everything in life, it varies with frequency, right? So therefore, the input impedance, the complex input impedance, is a function of resistance, which is a function of frequency. And we know that at the very least because we know skin depth, which we did in the previous few lectures ago, was frequency dependent, right? So therefore, you've got a frequency dependent loss, resistive loss, and then you've also got an admittance, which is also complex, which also depends on frequency, which could be either be inductive or capacitive, right? If it's positive, it's what? J omega L, right? So it's inductive. And if it's minus? Capacitive. Okay. All right. So all I'm saying here is, suppose we have an antenna and I'm making a very crude approximation to its input impedance, and I'm saying that it's frequency independent, or at least what I can say is at a particular frequency it has a real and imaginary component. Okay, now what I'll say, that real component of an antenna consists of two other components. We're talking about the real bit. Why don't we care about the imaginary bit? Like in a transmission line, or if you're doing even power systems, right? Why don't you care about the complex bit? And why does your electricity company ever charge you for the complex power that you are using? Sorry? Sorry? Is energy that you use. Yeah, the other one's just storage of energy. So your, I don't know, Origin or whoever you use as your city power, or whoever you use as your power, they only measure the real components, and that's what you get charged for. Anyway, so here we're looking at the resistive part, and we said the resistive part of an antenna consists of two components. The first component is the radiation resistance, and we'll talk a little bit about that in the next little while, and also the loss resistance. Now, we said that the loss resistance was due to skin loss and, and things like that, resistive loss in all the conductors. Now, can anyone tell me, why do I care about this? Why do I need to have the complex impedance of an antenna? Rather than, let's forget about the radiation resistance and the losses in the antenna. Why do I need to know this? It's not on this slide, so don't stress about it. Maybe it's on the next slide, but so why have your lecturers been harping on about complex impedances and all that kind of stuff, and transmission lines?
Because that's matched with what you connect the antenna to.
Why? Yes, why?
In order to avoid reflections and losses.
Reflections, yes, and losses, yes, and also maximum power transfer. All right, so therefore, and I'll derive all this for you again as part of your transmission lines, but that's the reason, right? That's when you're trying to transfer power, what you've got is you've got a generator, right? And usually a generator has an impedance, right? That's why usually when you grab a Keysight, they used to be called Hewlett-Packard in my age. Now they went to Agilent, then they went to Keysight. Now, if you grab a Keysight piece of equipment or whoever, usually a signal generator, it says this is the power and this is the source impedance also, right? So therefore what you need to do is the load needs to be connected, needs to be matched to that source impedance in order to be able to get maximum power transfer. And what I'll do as part of your transmission lines is I'll tell you why we've gotten this magic number 50 ohms for everything. Now, so this antenna has got this loss, but also this radiation resistance is essentially the component of power which is actually radiated. Right? Now, what we'll find out is that for certain structures, what we'll do is when we talk about, for example, small dipoles rather than large dipoles, that radiation resistance can be very, very small. What does that mean? It means that even though we might be putting a lot of power into that actual structure, or signal or voltage or whatever you want to call it, only a small percentage is radiated. It's a very inefficient radiator. So therefore, radiation resistance essentially tells us the amount of that power that we're actually putting in, what percentage of it or what component of it, or allows us to work out what component of it is actually transmitted out into the air as useful signal that our phone can pick up so we can do our weak chat conversation. Okay? Okay, so what I've done here is I've modelled this antenna as a loss, the radiation resistance, which we've spent a little bit of time describing, and the susceptance. Now, what I want you to prove for yourselves is, sorry, and there's a mistake in the slides. That should be P. Okay. The total power, right, that is radiated is just I half, and this is the average power, I squared radiation resistance. That's the actual power that's radiated. And what I want you to do is to convince yourself that this is actually the power that is actually delivered or transmitted. Right, that's just I squared times the radiation resistance. I've said that the model for this is literally just, guaranteed, if you tell me you haven't done this, I'm going to walk out, because I find that I just wouldn't believe you, right? If you've done 4 years or 6 years now of engineering and you claim that you haven't done this, I'll freak out. You've got your radiation, you've got your source, which has got a certain impedance. You've got your antenna, which has got the load, radiation resistance and susceptance. You can actually work out what the current is going to be given a voltage here. You know what a voltage divider is, and you also know that, since you know the total current times the I squared R is the power that's actually dissipated. That's all it's saying. That's giving us, if we had the radiation resistance, we can now work out what the power, the amount of power that's actually being transmitted. And essentially, the imaginary components, all I'm saying here is the imaginary components tells us or indicates to us the amount of power that is used to set up the fields and energy stored in the antenna. And remember when we were talking about near field and the like, and I said to you, in the near field there's the electric field and the magnetic field, and they've got all this complex structure, and they're very highly time varying, they're not very well defined. That X component is used to define, is essentially that energy that's stored or used to create those, the field in the, to create those fields. which we talked about are in the near field. Anyway, that's not particularly important, other than there's an important concept called radiation resistance. You need to know, if you work out what the radiation resistance is, that allows you to know what is the radiated power from that particular antenna structure. Okay, that's what's important. Okay, let's now move on. How much time we got? We got another 15 minutes, right? Yes? Come on, we can't let the enjoyment stop. Okay, now, in this part of the lecture, what I'm going to say is I don't need you to work out or know everything about radiation, auxiliary potential functions, other than this is how they're defined, right? So you can actually go through and work out what a Lorenz gauge is and work it all out. I don't need you to know this as engineers, right? At least as fourth year engineers. Sorry, you're not fourth years anymore. It's, what is it? Second year master's students. I don't need you to know that I need you to know that. The only thing I need you to know is there's this concept called vector potential, right? And this concept of vector potential is that if somebody gives me the current density, the vector potential is related to the current density through this particular integral, right? That's all I want you to know for this particular bit, right? So you can think of it as a God-given fact for the time being, right? So you can go and try to look up your physics books and look at your classical electrodynamics books, and they give you all the details on how to derive that. You can do that for interest, but for here, for this particular part of the course, or for this course, just assume someone told you, hey, vector potential is related to current through this relationship. And the reason why we need this is because we'll go through and talk a little bit about dipoles and work out how to be able to derive the radiation pattern, radiation resistance and the like for various types of dipoles. Okay, now let's talk about this little thing called an infinitesimal dipole. Can anyone tell me what they think I mean when I say we're going to talk about an infinitesimal dipole? Okay, so anyone? Everyone's looking down. All right, number 59, you're not looking down, so it's, what do you think I mean when I say an infinitesimal dipole? Yes, the number in front of you says 59, but you can't see it. You can say, I don't know, move on, and I'll find somebody else. Don't know? Okay. Anyone else want to have it take a guess? Yes?
An ideal lossless dipole antenna?
Okay. Close, but what we've got is, here we said that we've got a dipole that's lambda on 2 wavelength. In this particular case, what I'm saying is, suppose we've got a dipole, but instead of it being lambda on 2, let's assume we've got a little, this distance L is delta Z, where delta Z is very close to 0, right? Because think about it, right? One of the things that you want, if it could work for you, is to build the smallest antenna possible. Right? Now, the reason why we're going to go through this is, we're going to find out it's not particularly a useful antenna because it's not very efficient in the way that it radiates. But what's interesting is it sets up the machinery for us in order to be able to understand what radiation resistance is. It sets up the machinery in order for us to be able to calculate radiation patterns. It also sets up the machinery for us in order to be able to work out what the radiation pattern and radiation resistance is going to be for a much larger, more meaningful dipole, which is a significant portion of a wavelength. Okay? But where it's also interesting, now where it does become interesting is in AM, right, or short wave, where, if you're talking about 100 megahertz, if you had 100 megahertz, what's the wavelength at 100 megahertz? It's going to be huge, right? Many, 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 many meters, right? If you had a small dipole, which is usually dictated by a small percentage of a wavelength, what it also tells you is how efficient your AM receiver is to pick up a signal, right? Okay, so what we're saying is we've got this infinitesimal dipole here. Hopefully you can all see it. And what we're going to say is, in this particular case, we're going to assume this infinitesimal dipole has a current distribution on it, right? Now, usually what that means is, in most cases, you've got to work out, you don't know what the current distribution is, right? But in this particular case, I'm saying, well, let's assume that we have a current distribution. And usually when you're trying to work out the current distribution, what you're trying to do is work out what the standing wave pattern of the current is going to be on that particular dipole structure. Now, in this particular case, we're saying we've got an infinitesimal, and let's assume that the current density is as follows. Essentially, that the current is a blip, just positive, right? And we want to work out A, the radiated field, the power density, the radiation resistance, the near field pattern, and the far field patterns, all right? Now, as I said, I don't need, what I want you to just accept for the time being is that in order to calculate the vector potential, if I've got the current, there's a relationship between the two, and it's just a current, e to the j kr on RDL, which is over the length of the infinitely thin dipole, where R is the radius. Now, if you go through the process of doing calculating the vector potential and assuming that the distance is quite small, you can actually change dl to dz. R is assumed to be independent of z because z is so small, and you get a relationship that this vector potential is A of z, the unit vector in the direction of the z-axis, mu I naught lambda on 4 pi r e to the minus j kr. A lot of mathematics, not particularly useful at this moment in time. Now, what I'll do is, and again, I will do some maths. Now, most of this I don't need you to remember. What I'm trying to do, however, is just go through the process so at least you've seen it once in your lives on how to be able to derive the radiation pattern for a dipole. And what I'm doing is I'm changing, the first step I'm doing is in order to make the mathematics a little bit easier, I'm going to change from rectangular to spherical coordinates, right? And this is the transformation matrix. And we also know, because I said that this dipole is in the z plane, that AX equals AY, which equals 0. Now, if I put AZ in here, I can now get my radial and my azimuthal components, and A of phi equals 0. Now, if I go through some algebra, right, what you'll be able to show is the magnetic field is equal to this quantity, and, because there's no phi component, you can actually show that rho and theta equals 0, and h of phi, when you actually solve this equation, is equal to, gives you two components. Gives you a j, which is the complex component, k, which is your wave number, I naught L sine theta on 4 pi r, and then there's a bracket. There's a component which is I, plus 1 on j kr. Close the brackets, e to the j kr. So here, what we see is there's two components. There's the far field component, which radiates as 1 on r, and we also see there's a component which varies as 1 on r squared, which is your near field component. Okay. Likewise, if we go through this mathematics again, and we work out the electric field, We know that the electric field is related to the magnetic field through Maxwell's equations. Since we have H, we can now work out E, and we can work out both the radial and the azimuthal components. So if you go through the mathematics, you can actually show that these are the two relationships you get for a dipole for the radial field and the azimuthal field. And here, what you see is, for the radial field, you've got a far field component, which goes as 1 on r squared. Oh, sorry, no, it's still a near field component, which goes as on 1 on r squared. You've also got a 1 on r cubed. And the e to the theta is the only far field component that you get from this dipole. And then you've got r squared and r to the 5th terms. Now, from this, what we'll do is work out the power density, and we said that the power density was just simply the Poynting vector, which is E cross H. If you go through the algebra, right, as I've done here, you can actually work out the radial and the azimuthal components. And, if you do a little bit of simplification, you can actually work out that, the total radiated power is equal to eta pi on 3 I naught on lambda squared multiplied by what's in the square brackets here. And here what I'm saying is the power is the radiated power plus the energy stored in the field, which is the complex component. So now I know what my radiated power is. So my radiated power is eta pi on 3 I naught lambda L, which is the length of the dipole, on lambda, all squared. And we know, because of the way that we defined our radiation resistance, that's the same as a half I naught squared radiation resistance. Now, if you transpose, what you get is you get the radiation resistance is 80 pi squared lambda on L, all squared. Okay, now you say to me, Stan, that's a lot of work for nothing. Why did you do all this? Well, the reason why I did all this is so we can calculate, at least at the very first step, the radiation resistance of an infinitesimal dipole, a very small dipole. Okay. And if we go through this, and I said to you, hey guys, this dipole is a 50th of a wavelength, right? So it's very small, right? A 50th of a wavelength. What is its radiation resistance? What you see is its radiation resistance is 0.3 of an ohm. Okay. So what does that mean? If your source impedance is 50 ohms, okay, and your radiation resistance is, suppose it's a lossless antenna, right? So what does RL equal to if it's lossless? 0. So therefore, the only thing that we're getting is the radiation resistance. So therefore, the power that's radiated is only the power that it's I squared times the radiation resistance. Now, this radiation resistance is very small, which means only a very small percentage of the power is actually radiated. Most of it's lost in the source impedance of the generator. So it's terrible, right? Now, the point of all this is it allows you now to go, you've got a little bit of an understanding that, hey, I can't make my dipoles arbitrarily small because if I do, they're grossly inefficient. Now, you can say to me, well, maybe I don't care as much, right? Maybe they can be grossly inefficient because even though they might be inefficient, I'll make the other antenna much more powerful, but if I make this too big, well, it doesn't fit in people's pockets, right? At least this gives you the trade-offs and the machinery in order to be able to do the trade-offs, in order to understand how something radiates or doesn't radiate and how efficient it is. Now, we've got a few more minutes. I won't go into the next concepts because I think what I'd like to do is talk about it next at our next lecture. But what we'll do is then we'll talk about what the fields are in the three regions. So what I'll do is I'll talk about that in the next lecture. And at this moment in time, I'll open it up for maybe if anyone has any questions about what we've discussed about dipoles and antennas so far and radiation resistance. Okay, or maybe I'll ask questions. Yes, you can.
What's the reason that we wanted to test this?
Okay, so suppose if you could have an infinitesimally small dipole, okay, you want to have an AM radio receiver on your cellular phone, right? And we know AM radio stations operate at about 1 megahertz. All right, what's the wavelength at 1 megahertz? Very large, but tell me how to work it out. All right, we go C. All right. So the question was, why do we care about infinitesimal dipoles? Other than they're interesting, why do we care? Well, suppose, you know, AM radio stations or shortwave radio stations, you know, where you want large distances, what you want is to operate or transmit at very low frequencies. Okay? And usually AM radio stations or some of the, you know, the BBC, you know, where you're transmitting across the Pacific, or even some of the Chinese radio stations where they're trying to transmit across the Pacific, they operate at very low frequencies. So what we say is, let's assume the frequency is 1 megahertz, right? Okay, and we'll go through the reasons why, you know, you choose low frequencies. We know C equals FL, and it's 3 times 10 to the 8 equals 1 times 10 to the 6 times L. So L is 3 times 10 to the 2 meters, 300 meters. I don't want to carry a 300-meter phone with me, right? It's too big. I can't put it in my pocket. Okay. So I'm going to make the antenna on my phone, even if it's, this, you know, it's the whole edge, it's small, right? So for argument's sake, let's assume, what's this, I don't know, 0.1 of a meter? All right, 10 centimeters? I mean, this is very rough, right? So what we said was, hey, we know that the radiation resistance for this small dipole, which is what the structure that we'll use in here, is roughly 80 pi squared L on lambda all squared. Right? That's the formula. Hopefully I've got that right. Yes. So we got 80 times, for argument's sake, say 10, pi squared, 3.159 squared. I'm going to assume that's 10, right, for argument's sake. We're saying this is 10 centimeters, and we say the wavelength is 300. Someone has to do this calculation for me. Can anyone do that calculation? I don't have a calculator with me. Okay, so let's make this 80 times 10. Let's make that times 1 on 3,000 squared. 80 times 10 times, say, 10 on 3,000 squareds and 10 million, so I'm 10 times 10 to the 6. So 80 on 10 to the 6, which is 8 times 10 to the minus 5 ohms. Crap. But what it's saying to you is then you can actually work out what the efficiency of that's going to be. So it's going to be crap, right? But so therefore you need the signal to be very strong, and it also tells you how much of that is actually going to radiate or how much of it you're actually going to pick up. That's the reason. That's why you use an infinitesimal dipole. It's an approximation. But if you were now operating at 2.4 gig or 5 gig for your Wi-Fi, all of a sudden a wavelength is at 2.4 gig, if I remember correctly, it's 12 centimeters. Even so, if you had a half wavelength at 6 centimetres, well, all of a sudden that's a good, highly efficient antenna. All right, and we'll go through all the details there in the next in the next lecture. That's the reason why we're doing this. And it also gives us all the requisite machinery for us to be able to do a whole bunch of other stuff. Exciting? I think all this stuff's super exciting, but that's just